Ever wondered why a car overtaking you seems to be advancing at a snail's pace? That one's pretty intuitive. It's because you're also moving in the same direction. Your reference frame, or your perspective, is moving with the other car, so you only see a difference in your speeds. It's all relative, hence the name. And that idea seemed to be flawless until 1905, when Einstein put out a revolutionary paper that stated one important fact: that the speed of light was constant in any reference frame. This theory came to be known as special relativity. As a result, light's speed is now the universal speed limit. You can't outpace light, because it's always going to move at a constant speed relative to you, no matter how fast you're moving. But something isn't right here. Does this mean all the laws that we knew were wrong? Not really. Imagine your friend is in a spaceship moving at pretty high speeds and you're on the ground and you're both looking at the same beam of light. Since he's moving in the same direction as the light, you might assume that he sees light moving slower. But we just learned light speed is the same for both of you. So how? Isn't he moving in motion? The only plausible way to keep the speed of light consistent in this situation is if time progresses differently between both of you. If you perceive his time as ticking slower, then you can both observe the same speed of light even while moving relative to each other, since his seconds are now longer than yours from your point of view. But of course, messing with time leads to weird results, and what also happens is that you see his spaceship is shorter when it's moving to compensate for the time differences in his movement. Since his time is slower from your point of view, distance also has to contract, or his speed won't be the same as we see it right now. In general, light's constant speed messes with both time and length, but it also led to the most celebrated equation of the 20th century: E equals mc squared. Einstein found there was a link between mass and energy, with the speed of light binding them both. All of our nuclear energy is built on this one idea, that mass is linked to energy. But Einstein didn't stop there. Special relativity only dealt with constant speeds, but his new general relativity theory could deal with both acceleration and gravity, which are the same. Your friend drops a ball inside a rocket as he accelerates towards space. It falls to the ground. Did Earth's gravity pull it down, or did the rocket move up to catch it? The answer? There's no real difference. Both are equivalent. Gravity and acceleration are one and the same. This is the principle of equivalence. As for the workings of gravity, it was Einstein who suggested that the presence of mass itself warps the very fabric of space-time. We know big things attract more, so Earth literally bends space around it to change the path. The forward path that the object is traveling on now redirects to approach Earth. So let's assume your friend's in a rocket and let's drop a planet or two here and see how that affects his path. It's not so forward now, is it? Gravity literally bends space, and everything is affected by that change, including light. So if gravity affects light, then it must also affect time. So let's bring back your friend for a second. He's now in orbit. Between the two of you, his time moves faster. To see why, let us shine a laser at him. Notice how it changed color slightly? This change in color is because the beam has been affected by gravity. Gravity acts on this upwards moving light, but light can't slow down. Therefore, the light lowers in frequency instead, and the wave is stretched out to look longer. Anyhow, imagine that both your clocks are linked to this one light wave. In order to keep the relationship between this beam and the two clocks, his clock must be moving faster than yours in order to maintain the same flow of time with the longer wavelengths up there. As a result, time between both of you are different. So how does this affect us at all? Let's look at a real-world example, GPS. GPS relies on multiple satellites orbiting Earth that are both affected by gravity and also moving relative to the Earth, making it perfect to demonstrate the effects of both relativity theories. These satellites carry around extremely accurate atomic clocks, allowing position on Earth to be found by just calculating how long different signals take to arrive from different satellites. But as we know, gravity and velocity both have an effect on time in those satellites. So after scientists did some calculating with Einstein's theory, they found that clocks on GPS satellites actually tack on about an extra 38 milliseconds every day. And so they were able to fix it. If not, then your navigation systems would be completely off. Relativity allowed us to know why this was happening, and we might need it in the future if we go further into space. But this is only the beginning. Scientists are already starting to discover new things. Quantum mechanics, string theory. These things could change our understanding of the world as we know it. Again, just as Einstein did 100 years ago.